Hello everybody. Now let's continue discussing about arithmetic mean. Okay. So far we have considered what we usually call individual data. Now we're going to consider the arithmetic mean of frequency distribution. Okay. And the formula we've used for the arithmetic mean of uh, of a frequency distribution follows immediately from our previous definition. Okay. All right. The last time we just considered total number of values to be, if n was a given positive integer, then these were the values. Okay, these were all the values that were given to us. We did not consider any of them to be unequal. We didn't care if they were equal or unequal. Okay, now if this now for the frequency distribution, what we do is we consider that these values are distinct. Okay, each of the values are distinct from each other, they're not equal, and this value is repeated f1 times, which means x1 has a frequency of f1, this has a frequency of f2, means x2 is repeated f2 number of times. All of them are positive integers, okay, obviously, and this has been repeated fn times. All right, fn times. So the total number of observations are f1 x1s, f2 of x2s, and similarly up to fn of xn's. So if n is the total number of observations, then n will be the sum of these frequencies. Okay, f1 plus f2 plus fn, like this. Now to obtain the sum of these values, okay, the sum of these values, the average of these values, to obtain the average of these values, the arithmetic mean of these values, we need to find the sum of these values, the given values. Okay, the given values are we are given f1 x1s. Okay, how many x1s are there? There are f1 x1s. So we need to add x1 f1 times plus x2 f2 times, and proceeding similarly, we need to add xn fn different times, because x1 is given to us f1 number of times, x2 is given to us f2 number of times, and so on. Okay, xn, how many times? fn times. Okay, so this is basically f1 times x1 plus f2 times x2 plus fn times xn, so that average of these values, the arithmetic mean of these values, will be equal to the total number of observations, 1 over the total number of observations, times the sum of all the observations, which we found to be equal to summation I runs from 1 to n fi xi, right? So this is how the formula for the arithmetic mean of a frequency distribution is obtained. This is nothing but the individual, nothing but the arithmetic mean of individual sums, individual data. Okay, and we do it like this. If there are several different values, if a value is repeated several number of times, say for example 100 times, it will be time consuming to add, practically to add 100, the same value 100 times. Okay, 1 plus 1, or say let's say 2 plus 2 plus 200 times. The same result we can get the same result by multiplying 2 by 100. So this is basically for practical purposes, nothing much theoretical around here. And since this is basically the individual individual mean, the mean of individual data, all the properties we've discussed so far for the arithmetic mean of individual data will also hold true for a frequency distribution. Okay, now regarding the class interval, the frequency distribution involving class interval, to calculate the mean, okay, of a frequency distribution involving class interval like this, interval frequency and so on, all we need to do is to convert this into what do you call it, a frequency distribution of this sort by taking mid values. Okay, mid values. So it's basically the mean of this frequency distribution. So there's nothing more to discuss about this. Let's simply look at an example. Okay, a question. Let's simply solve a question right now. Yes, now let's look at this question. Okay, let's look at this question. So we're given a frequency distribution, and n is any positive integer. I forgot to write that. N is any positive integer, and these are binomial coefficients. Okay, NCR basically means n factorial divided by n minus r factorial times r factorial. Okay, that's all. Now before discussing the solution of this question, let's look at a well-known formula. We can prove it by induction, which we are not going to do right now. Okay, if n is any positive integer, then x plus y raised to the power n is equal to the sum of, let's use k. Okay, k runs from 0 to n, n c k, x raised to the power k, and y raised to the power n minus k. All right. So this is a well-known formula, and if in particular we choose x and y to be equal to 1, x equal to y equal to 1, then this will be 1 plus 1 raised to the power n, which means it is 2 raised to the power n, is equal to summation k runs from 0 to n, nck as it is, and x and y are 1, so we can omit this completely. So the sum of this binomial coefficients is equal to 2 raised to the power n. Okay, and similarly we can show that 2n minus 1 is equal to the sum n minus 1 nc n minus 1 c k. All right, that's it. We're going to use these two relations to solve this problem. All right, okay, now first of all, let's obtain the total number of observations. Total number of observations is equal to the sum of frequencies, okay, by definition. So this is equal to NC0 plus NC1 plus NCN, right? So this is basically K runs from 0 to N, NCK, right? And which is equal to 2 raised to the power n, NCK 2 raised to the power n. So we're basically done with the first part. Now all we need to do is to find the sum of the product of frequencies and observed values. Alright? So the total sum, the sum of all the observations is given by summation I runs from 1 to n. Sorry, I runs from, okay, this is x1, this is x2, this is x3, this is xn plus 1. Okay, so the total sum of all the observations, sum of all the observations is equal to 0 times NC0, okay, 0 times NC0 plus 1 times NC1, 1 times NC1 plus all the way up to n times NCN. Okay, so this is 0, so we don't need it. 1 times NC1 plus all the way up to n times NCN. Okay, so we can write this in the sigma notation as summation I is equal to 1 to n I times NCI, okay, 1 times NC1, 2 times NC2, all the way up to n times NCN. So I times NCI. Now let's look at this. I equals 1 to n I times this is equal to n times n factorial times I factorial times n minus I factorial. Okay, now this will be equal to I equals to 1 to n, since I factorial equals to I times I minus 1 factorial, we can get that I divided by I factorial will be equal to 1 over I minus 1 factorial. So we can write this as n over I minus 1 factorial n minus I factorial. Okay, now again using the same relation we can write n summation I runs from 1 to n minus 1 factorial over I minus 1 factorial. What the hell? N minus I factorial. Alright, okay. It's actually like this. Okay, it's actually like this. I'm writing n factorial as n times n minus 1 factorial. Since n does not depend on I, we can take it out as a constant. Okay, now let's see. If we take n minus 1 to be capital N and I minus 1 to be capital K, then n minus k is equal to n minus 1 minus I plus 1, which is equal to n minus I. So this is equal to n by n minus k factorial times k factorial, which means this is n c k. Alright, n c k, which is equal to this factorial is equal to this factorial, this whatever is equal to this thing, and NCK means n minus 1, C I minus 1. Okay, so basically this sum is equal to n summation I runs from 1 to n minus 1 C I minus 1. Okay, this one C I minus 1. Now let's change the index for a while. Let's say let's take I minus 1 equals to j. Okay, then since I belongs to 1 to n, j is equal to I minus 1. So I minus 1 will belong to 0, 1, n minus 1. Okay, n minus 1. So j will run from 0 to n minus 1. So we can write it as n summation j runs from 0 to n minus 1 C j. Okay, like this. So basically what we can say is this is, we keep n as it is, and j runs from 0 to n minus 1. This is something like this we discussed just now. Okay, n times 2 raised to the power n minus 1. Okay, so sum of all the observations is this much, and the total number of observations is this much. So the mean will be equal to the sum of all the observations over the total number of observations, like this. And we can cancel out 2 raised to the power n like this, which will mean that the mean is equal to n over 2. Okay, all right, that's how we calculate the mean of this frequency distribution. And I've been talking for 17 minutes already, almost 18 minutes. So let's stop it right here. All right, let's stop it right here.